Now we shall prove theorem 4 on homeomorphism. Now it states that a bijective function f from x to y is a homeomorphism if and only if for all subsets A of x, we have f of A interior is equal to f of A whole interior. Okay. Now, what is basically given? Basically given f from where to where? From x to y is bijective. This is basically given. And also there is if and only if in the statement. So we have to prove both necessary and sufficiency. So necessary, what is given? Necessary given f is a homeomorphism. What is homeomorphism? That is f is bijective, f is continuous, and f inverse is continuous, or f is an open mapping. Right? F inverse continuous is equivalent to f is an open mapping. Right? What we have to prove? TPT for all subsets A of x, we have to prove f of A interior is equal to f of A whole interior. Right? Yes. So now, so we have to prove for any subset A of x, no? So let me take any subset. So let me take some subset A of x. A is contained in x. Where will be f of A? F of A, of course, it will be in y. Image, no? So it will be in y. Now, since f is a homeomorphism, f is bijective, f is continuous, and f inverse is continuous, right? Since f is continuous, because f is a homeomorphism, since f is a continuous, do we know anything about interior? If f is continuous, will imply that f inverse B interior, remember this theorem, is contained in f inverse B whole interior for all subsets B of y. Remember this theorem? These two are equivalent. These two are actually equivalent. Correct, no? Now what do? We have a subset. We have a subset. See, this f of A, subset of y. Now in this, we are going to replace B by f of A. We are going to replace B by f of A. So replace B by f of A. Replace B by f of A. So wherever B is there, we are going to put f of A, right? So let me write what is the, LHS. LHS is f inverse. There is one bracket. There is one bracket, right? And inside, in the place of B, we have to put what? In the place of B, we have to put f of A. So in the place of B, we have to put f of A. Okay, and there is interior also. So B interior as it is. Interior as it is. Correct? So in the place of B, I'm just putting f of A. Right? Now this is contained in, this is contained in, okay. We have on the LHS f inverse, one bracket there. Okay, that whole interior also remains as it is. In the place of B, we have to put f of A. So in the place of B, I'm putting f of A. Okay, guys? Now, watch. We have f inverse and f. And whenever we have f inverse, f of A is contained in, or rather, what? These two are equal. No, why that is equal? So this is equal to, okay, the inside, this full part will be equal to A, and there is, interior here. That interior also follows there. Why these two are equal? Why this part is equal to this? Why this whole thing is equal to this A? Because F is 1, 1. Because F is 1, 1. Remember, whenever F is 1, 1, F inverse F of A is equal to A. Equality holds. Right? Okay. So now we have, let me rewrite it. So we have LHS F inverse F of A, okay, interior of this. Interior for this F of A, right? That is contained in, let me write the last part of the previous equation, that is A interior. Okay. Now we'll take F on both sides, or we'll consider images. We'll consider the images. So take the images now. So F inverse, F of A, whole interior as it is, right, is contained in image, right? So I should take F of A interior. F of A interior. Now you have F inverse. So F inverse of anything, now this is equal to F of A whole interior. Why these two are equal? Because these two are equal because our F is onto, bijective. Because, let me write that here, because F is onto. F is onto, so whatever the set F inverse, that set is equal to that set here, is contained in F of A interior. Right? So what we had to prove? We had to prove F of A interior is equal to F of A whole interior, right? But we have got one side and we'll call this as equation 1. We'll call that as equation 1. Now what is equation 2 now? What else we have to prove now? We have to prove the equation 2. What is equation 2? That is, we have to prove, so next, to show that F of A interior is contained in F of A whole interior. This we have to prove. So if you prove this, we can call this as equation 2, and 1 and 2 will give me that both are equal. That is what we had to prove. Correct? No? Yes. So now that is also very, very simple. So we have, what is the relationship between interior and the set? We know that A interior is contained in A, and next step, take the images. So F of A interior is contained in F of A. Agree? And what is A interior? Any set interior is open, right? Any set interior is open. So A interior is open. And what about F of A interior? And F of open set is open. Why? Because A interior is open. And why this is open here? Because F is an open mapping. Is open map. F is a homeomorphism, no. So F is also an open mapping. F inverse is continuous equivalent to F it is open mapping, right? So F of A interior, now look at this. F of A interior is one open set contained in F of A. What is the largest open set contained in F of A? The largest open set is F of A whole interior. So let me write that. So that is F of A whole interior is dash open set. What is that dash? Largest open set contained in f of a. This is largest, and you have, this is one of them. This is one of them contained in f of a, open set contained in f of a, and this is largest here. So combining these two, which is largest? This is largest, no? So which one will be contained in which one? So f of a interior will be contained in f of a whole interior. Correct? So we got equation 2. We'll call this as 2. By 1 and 2, they are equal. So by 1 and 2. By 1 and 2, these two are same. That is, f of a interior is equal to f of a whole interior for any subset a of x. Hence what? Necessary. We have proved the necessary. Now we shall go to sufficiency. Now can anyone tell me what is sufficiency given? So sufficiency given. What is sufficiency given, guys? Given for all subsets A of X, f of A interior is equal to f of A whole interior. This is they have given. What is TPT? To prove that f from where to where? From the domain X to the codomain Y is a homeomorphism. We have to prove this is a homeomorphism. That means we have to prove f is bijective, f is continuous, and inverse is continuous. So number 1, is it bijective? Clearly f is bijective. Why? Because it is basically given. I'll write within the brackets, it is given. What is the statement? Statement is a bijective function f, right? So f is bijective, it's already given. Second one, to prove that f is continuous. Show that f is continuous. F from where to where? From x to y is continuous. Prove that it is continuous. To prove it is continuous, we prove inverse of an open set is open. We prove inverse of an open set is open. So inverse of an open set is open, no? So where we have to take the open set now? So we have to take any open set in the codomain, that is Y. So let me take, let B be an open set in Y. Okay, and we have to prove F inverse B is open in X. Okay, yes. Now, yeah. Consider F inverse B. And where is F inverse B? F inverse B. Definitely, this is a subset of X. Correct? And what they have given? For any subset of X, what is given? For any subset of X. For all subsets A of X, they have given what? F of A interior is equal to f of A whole interior. And what do? Replace what and what? Replace, tell no. So replace A by F inverse B. Replace A by F inverse B. So in the place of A, we have to put In the place of A, we have to put F inverse B. In the place of A, we have to put F inverse B. So, let me write. So, F, put one bracket. Okay, in the place of A, let me write in black, that is F inverse B. This is our A. And there is interior here. So, interior as it is. Interior as it is. So, what that is, whatever is in black, no, that is replaced. In the place of A, I am putting F inverse B. And that is equal to, on the, this RHS. So in the place of A, I have to put one bracket here, and there is one more bracket, interior as it is. In the place of A, I'm putting F inverse B. Right? Now watch. You have F inverse. Whenever we have F inverse, there is a relation, right? And this that is equal to F inverse B is nothing but B. Is full inside. F inverse of B is nothing but B. Why equal? Because F is onto. Bijective, no? Onto. And the interior, this interior, no, will be followed. Because those two are equal. Whenever you have two, A equal to B, A interior is equal to B interior, no? Same logic here. We get this. Right? Now, in the next step, what do we do is, we'll take F inverse on both sides of this. So next step. So we'll take F inverse, the remaining as it is. So F, you have F inverse B of this interior as it is equal to, and F inverse on the RHS. So F inverse, and we have on the RHS, in the previous equation, that is B naught. Right? Okay, what is B? B is an open set. B is an open set, no. So what is B naught? We can write here. This implies B interior equal to B. Correct? Now, can you tell me what is that equal to now? F inverse B interior is nothing but B. Right? So what have we got now? So what is the LHS? So in the LHS, we have F inverse. Whenever we have F inverse F, and our F is 1, 1. So let me write that. Since F is 1, 1. So what? This is equal to, this is whole thing. Okay. This is F. Okay. This whole thing, right, will be equal to F inverse B, that interior follows, is equal to, why these two are equal? Because our F is 1, 1. Okay. Equal to F inverse B. I'm taking the last one here. That is F inverse B. So we have any set interior is equal to itself. Therefore, F inverse B is dash. F inverse B is open set. Right? What was B? B was any open set in Y, and F inverse B is open set in X. So inverse of an open set is open. Therefore, F is continuous. Therefore, F is continuous. F from X to Y is continuous. So we proved F is bijective. It was given already. We didn't prove it is bijective. It was given. And we proved it is continuous. Now we have to prove it is open mapping. To show that We have to prove F inverse is continuous, and we know that F inverse is continuous is equivalent to F is an open mapping. So we prove that F from X to Y is an open mapping. Is an open mapping. Okay, let me underline that. Right? Okay. That means what? We have to prove that F takes open sets to open sets. Okay, let me take any open set. Let U be an open set in the domain X. Okay, so since U is open set, what is U interior? Is U. Take the images now. F of U interior is equal to F of U. Okay, we'll call this as sum star. Fine, or equation 1, whatever it is. You can give the names. 1, 2, 3, 4, something like that. Okay, so now what is our U? Our U is any subset of X, right? Any subset of X. Then what they have given? Sufficiency given. So given for all subsets A of X, they have given F of A interior is equal to F of A whole interior. This is what they have given. Now what do? You just replace what by what? A by U. Replace A by U. Now in the place of A, we have to put U, right? So that implies, so F of, in the place of A, I'm putting U, interior follows, that is equal to F of, in the place of A, I'm putting U, whole interior. Now, what is U interior, guys? F of U interior is nothing but U only. Is equal to F of U whole interior. Right? What is the next step now? The last step. So that implies what? This implies whenever a set is equal to its interior, will imply that that set F of U is dash open set. F of U, no. So where it is open now? In Y. Right? So U is open set in X. So takes open sets to open sets. So therefore, F is an open mapping. Is an open mapping. Very, very simple. So by 1, that is F is bijective, 2, F is continuous, and 3, F is an open mapping, will imply that F is a homeomorphism. F is a homeomorphism, hence sufficiency. Hence sufficiency. Hence the theorem. So we completed theorem 4 on homeomorphism.